Hello students, uh, in this subunit I'm going to discuss electromagnetic radiation sources, that is sources that produce gamma rays or characteristic X-rays that come out from that source, and they can either come out from the nucleus or from the atomic shells. So electromagnetic radiation sources are of different kinds. First one that we can consider is the gamma ray after beta decay. That means a beta decay takes place, and after that beta decay, a gamma ray is produced because after the beta decay, the daughter nucleus is left in an excited state. Then another form of reaction that can produce gamma rays is annihilation reactions, in which a particle-antiparticle pair comes together and annihilate each other, and in the process they release gamma rays. Then in any kind of nuclear reaction like neutron bombardment or fission reaction, gamma rays can be produced as an aftermath of that nuclear reaction. Then there is a process called Bremsstrahlung, in which a charged ion can decelerate inside a medium, and in that process it produces gamma rays. Then of course you have characteristic X-rays which come out by atomic transitions between the different atomic shells, like the transition from L shell to the K shell or M shell to the L shell. So during those transitions, X-rays can be produced. Then you have synchrotron radiation, in which an accelerated charged particle which is following a circular trajectory, the time period of that circular trajectory can be varied with time itself. So the time period is changing, and during that process, uh, what happens is gamma rays are produced when highly energetic circular loops of electrons, they are accelerated in a circular loop, they can produce gamma rays. So now here, what is shown are different types of gamma rays uh, which are possible. Like for example, here Na22 converts into Ne22, but it does not leave the Ne22 in the ground state, but it leaves the Ne22 in the excited state. So a beta decay is taking place from Na22 to Ne22, and then the final daughter product is in the excited state, which is 1.274 MeV above the ground state. So 100% gamma rays with this much of energy, 1.274 MeV, is produced in this reaction. Another type of reaction that we can think of is cobalt 57, that converts into iron 57 through beta decay or through the emission of electrons. So characteristic electrons are produced, and the final daughter nucleus is left in two excited states. One is at 0.136 MeV and the other is at 0.014 MeV, and these two states produces three different types of gamma rays because of the change in these states from excited to the lower states. So one of them is the gamma 1 that is produced when the third or the most highest excited state of 0.136 MeV falls to the ground state, and in the process it produces a gamma ray of 0.136 MeV, which is just the energy difference between the excited state and the ground state. Similarly, gamma 2 is produced, which is of the energy 0.122 MeV, and it is basically a transition from the highest excited state to the second highest excited state. Similarly, a gamma 3 is also produced, which has an energy of 0.014 MeV. So the various branching ratios or the percentage of these different gamma rays that are produced is also shown in the bracket. 11% of gamma 1, 87% of gamma 2, and 9% of gamma 3 is produced. Similarly, you can talk about other reactions like, for example, cobalt 16 to nickel 60, and then also CS 137 to Ba 137, and so on. So gamma rays are produced through the radioactive decay of certain unstable nucleus. So common radioactive isotopes like cobalt-60 and cesium-137, we have discussed or we have shown these two decay schemes in the earlier slide. Other atomic decays are also possible, nuclear decays are also possible, releasing energy in the form of gamma rays. They include potassium-40, carbon-14, and isotopes found in the decay series of uranium, thorium, and actinium. The half-life of gamma ray emission following beta decay is extremely short. Now, this is an important point. The beta decay process has a very large half-life, whereas the gamma decay that is subsequent to the beta decay has a very short half-life, almost instantaneous, typically ranging from 10 raised to a minus 9 to 10 raised to a minus 14 seconds. So in many cases, it is so short that it is essentially immeasurable. When the nucleus undergoes beta decay, the resulting daughter nucleus often remains in the excited state, meaning it has got excess energy. To reach a more stable state, the nucleus can release this excess energy by emitting a gamma ray, which is a high energy photon. So this rapid emission of the gamma ray is a very quick process, and the transition time that it takes, that is required for such a process, is extremely short. Because the time taken for gamma rays is extremely short, the half-life of the gamma decay process is often just considered to be the half-life of the characteristic beta decay that is taking place before the gamma decay. So the energy level of the gamma decay is basically that of a daughter nucleus, whereas the half-life is that of the parent nucleus. So here you can see a cobalt-60 decay is shown. On the y-axis, the percentage of cobalt remaining is shown, and on the x-axis, the half-lives are shown. That is, 1 represent 1 half-life has been covered, 2 represent 2 half-lives have been covered, and 3 represent 3 half-lives have been covered, and so on. So 100, from 100 to 50, the cobalt takes about 1 half-life, which is 5 into 5.27 years. So in 5.27 years, the cobalt-60 becomes half, from 100 to 50. But that is the half-life of the beta decay, not of the gamma. So gamma decay has got a very short half-life, but understandably, we only take the half-life of the previous beta decay that is taking place before the gamma decay takes place, and that is considered to be the half-life of the whole process. Because the half-life of the gamma decay is so short, it does not contribute anything to the total half-life of the process. So gamma rays also come out through nuclear reactions. So for example, if beryllium-9 is bombarded with alpha particles, then it converts into carbon-12, which is in the excited state, and an neutron is also produced. Now this carbon is in the excited state, so it falls down into the ground state and produces an energy of 4.44 MeV gamma ray. The average lifetime of this state is so short, which is 61 femtoseconds. That means 61 into 10 raised to the power minus 15 seconds. So that is so short that it happens before the carbon, which is recoiling, stops. So carbon is basically moving while the gamma ray is emitted. So in the laboratory frame, the carbon recoils and the carbon is moving when the gamma ray is emitted. Because the emission process is so short, the carbon does not stop before it emits the gamma ray. So because of this, the source of the radiation is moving with respect to the lab frame, and because of that, the frequency of the gamma ray is Doppler shifted. So since the source is moving with respect to the lab frame, the frequency that we get is Doppler shifted and the frequency range is broadened. It is not monoenergetic, but a different range of a finite range of frequencies emitted, which depends upon the individual carbon atoms and their velocity with respect to the lab frame. So for several calibration purposes, for very highly accurate detectors with good energy resolution, this is difficult to measure because the energy resolution of good detectors is so good that some of the gamma rays will fall out of the range of the detection of the detectors because they are outside this range, because they are having a larger range than what the detector can detect because of the Doppler shift or the Doppler broadening, you can say. But in another possible reaction, like carbon 13 bombarded with alpha 4 gives us oxygen 16, which is in the excited state, plus a neutron. Now the oxygen 16 is now produced in the excited state of 6.130 MeV above the ground state, and this excited state has a lifetime of 2 into 10 raised to the minus 11 seconds. This lifetime is sufficiently long. It is quite long compared to a femtosecond order lifetime for the earlier reaction. So it eliminates all the Doppler effect because the recoiling oxygen atom or the nucleus stops before the gamma ray is emitted, because the lifetime of gamma ray is large. And so the resulting 6.130 MeV gamma ray is essentially monoenergetic and can be detected by high resolution detector. Similarly, gamma rays are also produced by absorption of thermal neutrons by some nuclei. So sources of thermal neutrons are basically intense beam from the nuclear reactor. So if something is happening in the nuclear reactor, a nuclear reaction is taking place, and that produces beam of uh, neutrons, which then interact with other material of the nuclear reactor and produces gamma rays. Similarly, accelerators or radioisotopes, which are moderated uh, in the nuclear reactors, those also produce weaker fluxes of neutrons, and these neutrons are captured by other material in the medium that is surrounding, and this nuclear capture renders those material in the excited state, and those material then emit gamma rays which have an energy as high as 9 mega electron volt.